have to do that for the pre-doc students, but I didn't think I had to do that with you guys. Let's do
We'll
it.
take it.
We'll take it, yeah.
You'll take it anyway? All right.
Yeah.
Does anyone know what is going on though? This is like
No.
No,
a third of the class is not here.
we are at late.
2/3 of the class is late.
Traffic? All right.
They're all gonna come in one giant group.
Yes, so if they all come in one group, then I'm likely to think, oh yes, probably a systematic factor like traffic. But if it's more, sorry, my mind works in beautiful ways. Let's get started though. We do have quite a bit that we want to cover. We want to go over that dependent sample t-test from last time and then introduce ANOVA for this time. This is when we have more than two groups or more than two factors. All right. I guess I don't really need this since there's nobody in the back, right? Is that fine? Can I not use this
I think you're good.
without it?
Yes.
Excellent. Now I've got another hand free. Take a look at this figure. On the x-axis, we have the number of tests of hypotheses you're conducting. So for example, think about your study. Your study might have at least one major hypothesis that you're testing, and then there might be another one, like an additional one, like a secondary one. Then on the y-axis, we have the probability of at least one p-value less than 0.05. And remember, a p-value less than 0.05 indicates that we've found something. There's a real difference, a real effect. And we hope that when we say that it's not an error. What kind of error have we committed if we say there's a difference when there really isn't one? What kind of error is that? It's either alpha or beta. Alpha, that's right, it's alpha error. So again, on the y-axis, we have the probability of at least one p-value less than 0.05. And we want to keep that alpha error somewhere around 0.05. Okay? But look at my y-axis. My y-axis is number of tests. Our our x-axis isn't the trueness of our hypothesis, right? It's just the number of tests I'm conducting. So, truth should be independent of the number of tests I run, right?
Yeah.
But that's not what we see here. What we see here is that the probability of a p-value less than 0.05, which is indicating we found something real, this probability seems to change with the number of tests I run. And that should not happen. Okay? So for example, kids, they want something. First couple times they ask for it, you think it's not a great idea, so you say no. But the kid knows, if I increase the number of times I ask, I will get the answer that I want, right? The same thing is happening when we're testing hypotheses. If I run a certain number of tests, the likelihood that one of them will show me that there's a real finding, even if there really isn't one, increases. So we have to figure out how to test our hypotheses so that this doesn't happen. That is, we go beyond this value of 0.05 just by the number of tests I'm running. Yes?
In this situation, are the test parameters changing or are they
No.
okay.
Just assume everything else is staying constant. The only variable that's changing is the number of tests I'm running. So if I've got this really big, large study, and I'm running like 13 tests, and I don't know how great your approximations are for figures that are 10, 12, 15 feet away, but 13 puts us where on this figure? 13 puts us around where?
0.42.
Right. So if I'm running at least 13 tests, so if you're reading an article and you see 13 p-values at least or more, that means the likelihood of a p-value being less than 0.05 was close to 50%, somewhere between 40 and 50%. It's almost like a coin flip. Those are not the probability levels that we want to deal with. We want our alpha error no more than 0.05, and we want it to stay there regardless of how many tests I run. Okay. You with me so far? That's why we're going to learn how to run an ANOVA test, an ANOVA procedure, which says, hey, if you've got more than two groups and you're going to end up wanting to do A versus B, A versus C, B versus C in terms of comparisons, for example, that's more than one test. So the ANOVA procedure says we're going to look at our data another way so that we don't go above this 0.05 level in terms of alpha risk or alpha error. The ANOVA procedure is also really good if you have more than one hypothesis that you want to test. Oftentimes there's more than, for example, if you think about variability as a pizza pie. Variability, right? So for example, when you take your final board scores, hopefully you all will pass, but if it's a continuous level, you all will get different scores, right? The variability in those scores, why you're not all the same score, why did that happen? What are the factors that influence why all of your scores are not the same score? Is there only one factor? No, multiple factors. So when we're thinking about variability, especially in our dependent variable, there are multiple factors involved, and those are the slices of pie. So the ANOVA says, hey, let's think of all the slices of pie that are possible here for accounting for this variability. And it'll test to see which ones are significant and which ones are not. All right. So all of this is supposed to help us to be able to consider geographic variation where we can do this. We can take the West and compare it to the Midwest. We can take the West and compare it to the Northeast. And we can take the West and compare it to the South. And take the Midwest and compare it to the South, Midwest and compare it to the Northeast, and South compared to the Northeast, right? That's more than one test. We want to be able to do all of these comparisons without increasing alpha error. So we're going to have to use a procedure that we haven't learned yet that allows us to do that. That's called the ANOVA procedure. So we're going to run through these same steps again. We make our assumptions, we state our null hypothesis, we figure out the sampling distribution that we need, we compute a test statistic with Jamovi's help, of course, and then we're going to conclude, make a decision based off of the results that we have. But before we do that, I want to answer up some questions about the dependent t-test. Now the dependent t-test is very similar to the one sample t-test. The dependent t-test, you have two groups. Now in our example from before, those two groups were two different time points. Okay, two different time points. So for example, we have the proportion of kids receiving preventive dental care. We've got it for 2007, 2011, and 2016. Those are 3 different years. So if I wanted to compare and see if there was a difference from 2007 to 2016, right? Since the same states are participating, I can use what's called a dependent t-test. The independent t-test says, no, your two groups must be different. So when we took all the states and we split them up into states that had affordable health care and states that did not have affordable health care, those are two separate groups. You can only be in one group. But the dependent t-test says, we're going to use the same groups and either watch them over time or take a group, provide an intervention, and then measure that group again. This dependent t-test is a really smart way to look at the signal-to-noise ratio. Why do you think the dependent t-test is stronger than the independent t-test when you're testing hypotheses? So for example, if you wanted to determine whether a particular treatment was helpful, you could either take two different groups, and in one group, you give them the new treatment, and you compare the results between both groups, or you can take one group, measure them at a baseline, and then intervene, and then measure that same group again. Which of those two setups, which of those two methodologies would be stronger, and why?
Independent.
Okay, yes, I agree with you, the dependent. But why? Why would the dependent be stronger than the independent?
Proves causation.
If this were a trial, yes, this would be a really nice example of causation, if this was an experiment. But if we think about what we're going to be looking at, which is, let's say 2007 for proportion of kids receiving preventive dental care, 2016, that's not an experiment, that's just an observation of survey data. But why is that stronger than, let's say, an independent design?
Because you have more data that pertains to each state.
We do have more data, but the more data that we have isn't exactly obvious. The more data that we have is, when I measure you at one time point when you were juniors, measure you again when you're seniors, the assumption is whatever is unique about you stays constant. And whatever changes is probably due to whatever it is I'm looking at. So for example, if I'm looking at the Affordable Care Act, and I think that because it came in 2010, it's going to influence what happens from 2007 to 2016, that means 2007, without the exposure, 2016 after the exposure, whatever was unique about Missouri or Nebraska or Pennsylvania or Oregon, whatever's unique about them stays the same. But whatever changes, I'm going to say is due to something like the Affordable Care Act. Okay? So the dependent design is really strong because it says mathematically, statistically, whatever is unique to you, your variability, I'm going to hold that constant because I see it 2 times. If I hold that constant, whatever else is above that, I'm going to say it's due to some other factor. And guess what? If that other factor doesn't really do anything, then you look the same at the beginning and at the next time point. This is very strong because of that. In fact, it's so strong that you only need a smaller sample size to test here than with the independent sample t-test. So if you assume everything else is the same, the dependent t-test only needs a smaller sample size to test the hypothesis than the independent t-test. Because there's so much power in being able to say, hey, I see you here and I see you at the follow-up. I know what's the same about you. So now I can subtract that out. So what are the assumptions for this test? The assumptions for the dependent t-test, also known as the repeated measures t-test, is that 1, independent and random sampling for the population of interest. Dependent variable is normally distributed, and dependent variable has to be measured on a ratio scale. And now when we say that the observations are independent, again, we're not talking about the dependency between the 2 groups. We're talking about the fact that when you go into the sample, right? You go into the sample and you randomly select, we're going to get that nice probability curve. But the independence also comes from the fact that you're not, I mean, you can be in 2007, 2016, but you are not influencing the results of anybody else. Okay, so Missouri isn't going to influence California. Shouldn't influence any of its neighboring states either. Here we're gonna for the independence for this dependent t-test, that's what the independence will mean here. Yes. Right. So clearly we have more than one observation, but you are not allowed to influence anyone else's observation. Otherwise, we would violate. This would then violate our random sampling. Okay, so when I ran one sample t-test, this is a couple of years ago, for the change from 2007 to 2015, proportion of kids receiving preventive dental care, this was the distribution that we saw. And one of the things I wanted to do here was from 2007 to 2015, those are 2 different time points, but I made them one variable by simply subtracting. Okay, so Missouri in 2015, Missouri in 2007, if I simply take the delta, if there's been no change, what should my y-axis be? If there's been no change from 2007 to 2015?
0.
0. So here we have this reference line that says when there's no change, no difference between 2007 and 2015. So now it makes it a little easier visually to look at the box plots and see how close to this 0 they are. So for the West, we can see that it's not close to this 0 at all. The median is above, so there's been a positive change. More kids are receiving preventive dental care from 2007 to 2015. In the Midwest, however, we're not close to the 0, especially for that median, and it's in the opposite direction. Fewer kids are receiving preventive dental care. In the South, more kids receiving preventive dental care. And in the Northeast, describe what you see here for the Northeast. How would you summarize that? Sorry?
more or less stays the same.
More.
Okay, so it's harder because if you look at this blue box, and what do we say, how much is in this blue box? How much of the distribution is in this blue box?
The inner 50%.
Inner 50%. So the middle 50%. We can see that the middle 50% is both above, that is, there are some states that are improving, and some of them are getting worse. But the median is where?
Above.
The median is above. So overall, central tendency, the median says it's above. But if you look at the middle 50%, it says, well, some of the states are improving, and some of the states in the Northeast are not improving. They're getting worse. But our goal is to find out which of these is statistically significant. And we can see here that for the West, although it is above, the p-value is only 0.067, so it's close to rejecting the null hypothesis. It's close to saying that, oh, this difference, this improvement that we see in the West is significant. It's close, but not quite. Then for the Midwest, it got worse, and its p-value says that was significant too. It's less than 0.05. For the South, improvement overall, and it's significant, p-value 0.004. It's less than 0.05. And then for the Northeast, mixed bag. And this p-value kind of reflects that. There's no significant difference from no change. But if you look at the variability, everyone isn't right here. We see that some are up here and some are down here. So oftentimes you can't just look at the median to get an idea. Right? Sometimes you need to look at the median and the spread. Central tendency and the spread. Okay, so the p-value here, 0.890, which says no statistically significant difference from 0. Okay. So that's the repeated measures, or dependent t-test. Do we kind of get an idea of what's going on there? Somewhat? Okay, somewhat. When we work with it in Jamovi, then it starts to make a bit more sense. I want to introduce the one-way ANOVA, and then let's get into Jamovi and start running the one-way ANOVA and the dependent t-test. The null hypothesis for the one-way ANOVA is following. Mu sub 1 is equal to mu sub 2 is equal to, let's just say mu sub I. We don't know how many groups we're going to have, but we know that it's more than 2 groups. So we're going to just put mu sub I. The null hypothesis, though, is that all of those means, all of those populations have the same mean. That's the null hypothesis. The alternative would be what? How would you reject this hypothesis? You remember when we did that? One card has a vowel, another card has a consonant, and if you flip those around, one of those cards has a even number, the other has an odd number. And we were trying to determine whether you have to flip over all the cards, only some of the cards, and which cards. How would you reject this? How would you test this idea? Not all of them are equal. So all of them are equal, and all of them are not equal, or at least one pair is not equal. Yes, at least one pair. Because we only need one of these groups, the comparison to not be different to reject this idea. Okay? So not all of them are equal. We've been dealing with signal over noise ratios as our statistics. So we had a Z, we had a T, we now have an F. And it's still the same. It's still signal over noise. But the difference here is instead of looking at the central tendencies directly, we're going to use differences among the central tendencies to give us dispersion or variance. So this test is actually called analysis of variance. It's not analysis of means. We're comparing the means, we're testing the means, but we're doing so by looking at the variance. So the way the ANOVA procedure works is it takes all of your data and throws it into one big bucket. So again, you have multiple groups. All that data goes into one big bucket. And that one big bucket, you calculate a mean for that big bucket. Then you try to find out for every single group that you have, how far away is the group's mean from that big bucket mean. We got that so far? That delta that difference is what you're going to square and then sum them up. That's the numerator. That's the signal. Again, I've got more than two groups. Let's say we've got 4 groups. West, Midwest, South, Northeast. Take everyone's data and throw it into one big pot. So it's the US. But throw it into one big pot. Calculate a mean for that one big pot. Then split all the data back out into the groups and calculate the means for the groups. And find out how close is the mean for the group to the big bucket mean. Some might be close, some might be far away. But however far away they are, we calculate that delta and we square it. Remember, just like we were calculating variance, standard deviation and variance, we do the same thing for this analysis of variance. Why do we square these deltas? Do you remember why? Why do we square the deltas?
We can have negative values.
To make them positive.
Right, so we can have values to work with to make them positive. So if we do not, then they're just going to cancel them out. Right? The negative ones will cancel out the positive ones and we'll be left with 0. Well, we actually want to calculate the amount of variance here, so we're going to square all the deltas. Okay? So that's the numerator. The denominator is within each of the groups, there's variance. Right? Like the Northeast, very homogeneous, as compared to the South, very heterogeneous. So every group has their own standard deviation and variance. And again, we do the same thing. Variance for the entire big pot. Then we find out how far away the variances are from the group, for the groups, from the big pot variance. That's within group variance. So between group over within group, signal over noise gives us this new statistic. And it's called the F-test. Now you won't have to do this by hand, but we just want to understand what Jamovi is doing when we tell it to run it for us. Okay, so this is how you actually keep track of when you're calculating it. You're not going to have to do this. I just want to show you what's happening for you when you ask for an ANOVA procedure. So what you want at the end is over here in this F column, right? It's your between group variation over your within group variation. I just want to demonstrate to you that simple arithmetic is all that's needed to do this. So how do I get the mean squares for the groups in my numerator? Well, I take the sums of squares for the group, and the sums of squares is just, again, how far away are the groups from the big bucket? And we sum up those squares. So I take those sums of squares and I divide by degrees of freedom for the groups. Now, the degrees of freedom, remember, is our handicap. We want to run a test, but we statistically handicap ourselves. So, for example, we take 1 away for every group. We have 4 groups here: the West, the Midwest, South, and the Northeast. Right. So 4 then becomes 3. Why is that important? What effect does that have when I take away sample size? What effect does that have? Does it make it harder or easier to reject the null hypothesis when I do that? It makes it harder. Do you know why it makes it harder, though? Why does it make it harder when I take sample size away?
Is that what you compare it to?
Sorry?
Is it that what you compare it to?
Yes, so it becomes more unclear what I'm comparing it to. Right, so for example, if you wanted to know something about a population, but you only had access to a sample, the larger your sample is, the more you approximate the population, right? But if I take away from my sample, the smaller my sample is, the more uncertainty I have about my population. Right? So when we say, okay, you've got 4 groups, but take 1 away. So I have 4 groups, I'm taking 1 away, I'm making it harder. But that's okay. We feel like we still have enough. And then for the within group, we do the same thing. How many states are participating in each region? And for every region has to give up a state, or at least give up a sample size. Give up 1. So you might have 4 or 17 states in your region, you have to give up 1. Now you only have 16. You might have had 9 states in your region, now you have to give up 1. Now you only have 8. When we keep doing that, we keep making it harder. Not too hard, just a little bit harder because we say, I don't really know what's going on. I don't have the full population, so I'm going to make it just a little bit harder. And if I still find that there's a difference statistically, if my p-value is less than 0.05, I have a lot of confidence in my results, knowing that I handicapped myself. All right, so what are the assumptions for the ANOVA procedure? First, independent and random selection of subjects. Dependent variables ratio. Dependent variables normally distributed. This would be the proportion of kids receiving preventive dental care. Okay. Its ratio level, it's normally distributed, and a new term, homogeneity of variance. Homogeneity of variance. What does homogeneity of variance mean? What do you think that means? Same, yeah, the same variance, the same structure for the variance between or among the groups, since we have more than 2 groups. So we're going to test for homogeneity of variance, which is another way of saying, do your groups have the same last name? And if so, yes. Now we can see if the first names are different. If the first names are different, then we're dealing with different people. If the central tendencies are different after we've assumed that the variances are the same, we're pretty certain that we have different populations. All right, so these are the results. This is how you write the results. Okay. I want to go through that very quickly, and then I want to show you how to get to the results. So we'll run the Jamovi after we do this. There was a statistically significant difference between groups as determined by one-way ANOVA. So F, which is our test statistic, 3 and 23.6. The 3 is the between groups degrees of freedom. I had 4 regions, and I had to give up 1. And the 23.6, it's not as rough as the between group variation, but this is also every group has to give up 1, and there's an additional correction factor. And so we end up with only 23.6 for our within group degrees of freedom. But this F statistic is now 5.16. Okay, and this 5.16 is bigger, it's more extreme than what we expected, and that's why our p-value is less than 0.05. Tukey post hoc test revealed that the change in percentage of kids receiving preventive dental care from 07 to 16 was statistically significantly lower in the Midwest as compared to the West and the South. And inside of here, what we put is the actual percentage difference for kids receiving preventive dental care from 2007 to 2016 and the standard deviation, so plus or minus the standard deviation. Then we follow up with there were no statistically significant differences between Midwest and the Northeast, South and the West, South and the Northeast, and Northeast and the West. So we start first by identifying where do we have significant differences, and then we end with where we didn't have any significant differences. Okay. Sort of straightforward. Okay, now we have to figure out how do we actually get here so that we can build these kinds of statements. And again, I expect you to copy these statements word for word and just swap out variable names, swap out, means and standard deviations and p-values. Okay, but keep the structure. This is how we report. You just swap out what's unique for your situation. Okay, so now you want to bring up your Jamovi. Let's figure out how we get here. You should have received a new lab document. Did you get a new lab file? Yes? Anyone having difficulty opening it? No?
It goes right to Jamovi, right?
Should go right to Jamovi. So in the beginning, I wanted you to get some practice bringing in the CSV files. Now that you should be pretty good with that, now you can just take a Jamovi file straight, open it, and get straight to work. Okay, Jamovi up and running? Almost. Okay.
Go ahead, Bill.
Getting some head shakes. Yes? else getting a document preview?
It won't let us know.
What's the name? What's the name?
You have an error? Who has successfully downloaded it? Okay, half the class. Maybe log out
So
from.
it says, the document preview is currently being processed, please try again later, so it won't even.
I just
preview
ignored
it
that.
or-
I just clicked the link and it took me straight to Parallels.
You have parallels, you don't have
See
Oh,
if
some
it'll
of
just
you don't
go
have
straight to your
Parallels?
app. See if it'll take you straight to Jamovi.
And yours is open? Yes.
On mine, it says, dependent variables, and then the grouping variable, it's not on mine. Is there a way to get that on there? The grouping variable?
Right, so we're going to have to go to One Way ANOVA. Are you in One Way ANOVA? Yeah. All right, for those of you who are having difficulty downloading it or opening it, talk to one of your neighbors and see if you might be able to follow their steps. Yes, no, please. Oh, you're just stretching. Okay.
I just dragged it.
Just drag it over into Jamovi? Yeah.
Mine, I'm dragging.
Thank you.
All right, so I'm going to go ahead and get started
It works when I.
when you drug it. Top left. You'll see one of your drop-down menus is ANOVA, analysis of variance. That's it. That's what you want to select, ANOVA. Okay. When you select ANOVA, the top option,
One way.
One Way ANOVA, yes. The one-way ANOVA simply says there's only one factor, one independent variable here. Okay, that's the one-way ANOVA. For example, down here we see repeated measures ANOVA. The repeated measures ANOVA says that one variable is a dependent variable. So for example, if we're going to do 2007, 2011, 2016 as a one-way ANOVA, we would choose a repeated measures ANOVA. Okay? But we're not using time as our factor of interest. We're using region, and that region variable has west, Midwest, South, and Northeast, 4 levels. Down here, we also see ANCOVA, which is analysis of covariance. And we can do an ANOVA procedure, but what it also allows us to do is to add a covariate measure. And that covariate measure allows us to kind of make our groups have a fair comparison. Weight loss studies or exercise studies, for example, if you're trying to build strength, some people naturally are stronger than others, right? So how would you make them all the same when you start your study? So everyone's gonna be on the same program. But again, some people are stronger naturally than others. How would you statistically make them look the same, as if they all started from the same position? How would you do that?
Baseline.
Right, so everyone's going to start at baseline. Let's say this is a 6-week trial. Everyone starts at time 0, day 1. But how do we account for the fact that some of you guys have been working out for 2 years and others haven't, or some of you are just more naturally stronger than others? How do we account for that? Subtract their...
Like the results, so it's like you see the improvement.
Right, so we use another word for that, and it's called adjust. So instead of subtracting for their strength, we adjust for it. The way we adjust for it is with this covariant. So what we do at baseline, we say, okay, we're all going to give you 45 pounds maybe to lift, and we'll see how many times you can lift 45 pounds. And that variable we'll use as a covariate, as a proxy for how strong people are when they start the study. That way, when we look at them at the back end of the study, statistically, we've adjusted for the fact that everyone starts from a different strength level. Okay? So that's analysis of covariance. And there are some other more special ways that we can modify this ANOVA procedure, but it's a very, very powerful procedure. So when we select the one-way ANOVA, you should get a window. Thank you for joining us. Everything okay? Good. Oh, no special story. No? I'm just giving you a hard time. I haven't seen you guys in 2 weeks, and it's all pent up, so got to pick on someone here. In our one-way ANOVA procedure, we see this window here, all the same variables you had before, but you should notice that you've got 3 brand new variables, right? So at the back end, did you notice those guys? Right. So what we did is we created delta variables. We calculated the difference for each state from 2007 to 2016, 2011 to 2016, 2007 to 2011. Why do you think we did that?
So you can compare them.
Yes, so we can use them, we can compare them. There are 2 big reasons why we did this. The first is to make it easier for us to look at the changes. So we're interested in change over time. We're also interested in the regions. And we want to compare the regions based on how they changed over time. So the easiest way to do that would be to take one of those variables and to simplify it. Make 2 variables, 1. So that's what we did with 2007, 2016, 2011, 2016, 2007, 2011. 2 different variables, take a delta, now we only have 1. It's fantastic. Okay? But why do we split here, 2007, 2011, 2016? What are we really trying to get at here?
To compare 2007 with 16, 11 with 16, and then see if 11 and 7 are equal or not.
Okay, and so what would that tell you if they are? So for example, look at them. We have one large span, 2007, 2016. We have 2 shorter spans, 11 to 16 and 7 to 11. Why would those be meaningful? Because what are we trying to get at? What are we trying to figure out here?
There's improved.
Yes, we're trying to determine if there's change, significant change, perhaps improvement. But why these time points, aside from the fact that that's the data that was available to us? What are we really trying to test here? What's our big idea here?
Oh, we want to see overall from 2000 to 2016 if there was a change, and then we're going to look at changes within that change.
Keep going. If there was a change, what would we attribute it to?
The ACA.
Right, ACA, the Affordable Care Act. So here we have 2007, 2016. We have the big, large time span that encompasses where the Affordable Care Act is, right? Right there in the middle, around 2010, 2011. Then we have before the Affordable Care Act, or just around there, 2007, 2011. We want to see if there's any change there. If there's change before the Affordable Care Act, how do we factor that into our interpretation? If we find that there's change here.
So it was better before.
Maybe. But if we're saying the Affordable Care Act is going to change the proportion of kids receiving preventive dental care, but we see change happening before the Affordable Care Act, can we really attribute change to the Affordable Care Act if change was happening before the... Right, exactly. So we want this interval to kind of find out, hey, what was happening before ACA? Then we have 11 to 16 to say, hey, what was happening after ACA? And 2007 to 2016 to kind of get a general idea of exactly how much change happened from before ACA to after ACA. All right, so those are the 2 big reasons why we've created those variables for you. Let's deal with the largest one. Did we have any change from 2007 to 2016? So we take 2007, 2016, we make that our dependent variable, and what will our grouping variable be? Region, exactly. We are trying to compare our regions based on the change in the proportion of kids receiving preventive dental care from 2007 to 2016. One of the other differences that you might notice for your variable 2 is we're not dealing with proportions anymore. We actually converted them to percentages. That'll make it easier for you to interpret what's actually happening when you say, hey, this is the percentage amount of difference instead of proportion. Okay, so in order to get what we need to test our hypotheses, we need to start filling in some of our options. So on the left-hand side, where we see variances, we have 2 states. We have where we have equal variances and we have unequal variances. We need to figure out whether we have equal variances or unequal variances, because that will change the way the statistics actually run. Slightly, but sometimes meaningfully. So in order to test whether we have equal variances, we're going to use Levene's test. And so down over on the right, where we have our assumption checks, we need to ask for an equality of variances assumption check. So let's select that. Equality of variances assumption check. And you'll notice on the right-hand side, you should get an update in your window. So for your one-way ANOVA, come down to assumption checks, and here we've got the results for Levene's test. Now, the null hypothesis for Levene's test is homogeneity of variance. The variances among the groups are the same. West, Midwest, South, Northeast, they all have the same amount of variance. Okay? The p-value here says 0.464. So what do we do to that null hypothesis of homogeneity of variance? Keep it or get rid of it?
Keep it.
Keep it. This p-value is greater than 0.05, so we keep the null hypothesis, which is homogeneity of variance. If we had to reject that null hypothesis, if this p-value were less than 0.05, we would be concluding heterogeneity of variance. Different variances. Or at least two groups with different variance. Okay? So now that we know we have equality of variances, over here we want to run our test with equal variances or unequal variances. Which one?
Fisher.
That's right, equal variances. So select Fisher, where we can assume equal variances. Now some of you are extremely thorough clinicians, or very thorough when it comes to your work, and so you're asking yourself, well, couldn't I also just select unequal variances too, just to kind of see if the results would be different? And yes, in practice, that's what we do. We look at our results and we try to determine if there are differences when we assume another state. Right? So go ahead and select both, even though we only want equal variances, select both so we can get an opportunity to compare the results, compare the findings. Great. Over on the right-hand side, where we're asked for additional statistics, if you remember the write-up had central tendencies and dispersion. It had the mean plus or minus the standard deviation. To be able to get that, ask for a descriptives table. Okay? And you can ask for descriptive plots too, if they're helpful for you to understand where there are differences and where there aren't. Next, when we think about the assumptions that we were trying to run, first, we selected for equality of variances. We also have to make an assumption about normality. This is a new variable for you. You've already looked at proportion of kids receiving preventive dental care, 2007, 11, and 16. But now this is a delta, a subtraction, a difference. We haven't really assessed or evaluated the normality for that. So why don't you go ahead and select that too? Normality, Shapiro-Wilk. And we want the p-value for that to be what?
Less than
Exactly,
0.05.
greater than 0.05. Okay, we're almost there. Then finally, at the bottom, you see a group called post hoc tests. The ANOVA procedure evaluates your hypothesis in two ways, or in two steps. The first is, say, at a very high altitude, when we look down, do we see any differences among your groups? If the answer is yes, ANOVA will say, well then you need to conduct post hoc tests to find out which groups are different from each other. It might not be all of them are different from each other. Okay, so the first test is called a family-wise test. That high altitude test is called a family-wise test. Okay? And then if that family-wise test, if the p-value is less than 0.05, then you go and you run post hoc tests. So we're going to assume that we might find differences. We're going to go ahead and state which differences we want, or at least the types of tests that we want. And you can see that, oh, I heard it. What did you say? Tukey. We want Tukey. Why do we want Tukey? Or you just like the name Tukey? You just couldn't help but just, I gotta say that. Tukey. Tukey.
No, it's in the reporting results.
Yeah. It's from that slide. We saw Tukey results. We want equal. We want Tukey because we have equal variances. So since we have equal variances, select Tukey. If we did not have equal variances, can we still run our test? Yes. We'll use Welch's test for our one-way ANOVA result, but we'll use Games-Howell for the post hoc comparisons. Okay. So go ahead and select Tukey because we do have equal variances. Tukey. And then finally, when we're comparing West versus Midwest, West versus South, West versus Northeast, etc., etc., we want test results. That's the T and DF. That T is a statistic that you remember. That's a T-score, because now we're looking at two groups. It's West versus Midwest. So now we can use a T statistic. And we'll get the degrees of freedom for that. And then we can also flag significant comparisons. Once we've selected those two, we are done. And Jamovi should, in a matter of seconds, also be done. All right. The data that we need to fill in that slide for what were your actual results. This first table is the most important table. These are your ANOVA results. And if you want to jump to the punchline, go all the way over to the end where you have the P. That's your P value. Now you'll see two P values because you selected two different ways to assume, to make assumptions about your variances. The top is Welch's, and that's for we're not going to assume equal variances, so unequal variances, or heterogeneity of our variance. The bottom is Fisher's for equality or homogeneity of variance. Now, we have homogeneity of variance. Our p-value of 0.464 tells us that. So which of these rows do we want as our official results?
Fisher's.
Top or bottom? Fisher's. And what's the result for Fisher's test? The p-value, what does it say? 0.005. So do we have statistically significant differences among our groups?
Yeah.
Yes. Do we know which groups? No. This is just the family-wise test. High altitude. Are there differences down there? Yes, there are differences down there. Now you can go run post hocs to find out where those differences are. Notice the results for Welch's test. What if we didn't assume equal variance? What would our conclusion be then? Would we still have differences? Yeah, we would. But see how it's the p-value is a little bit bigger? There's a little bit more uncertainty with unequal variances than with equal variances. I mean, it doesn't seem like a lot, but that's what happens when we go with unequal variances. It costs us a little bit more. It's okay. We still have the same result here. There are differences. With me so far? All right, what about our descriptives table so we have an idea of what kinds of differences there are? This table, the ANOVA table, tells us you have differences. The descriptives table tells you what kinds of differences you have. So look at the West. How would you interpret this column where it says mean? These are percentages now, no longer proportions. These are percentages. How would you interpret this? What does this 3.077 mean? If we rounded it, it's 3.1. What does that mean?
On average, there was a 3% increase.
That's right. On average, for that region, they saw a 3 percentage point increase in the proportion of kids receiving preventive dental care. What about for the Midwest? What happened in the Midwest?
Just crazy.
Yeah, it went down, opposite direction, went down. And what was its mean?
Plus,
Just under 1 percentage point. Just under 1 percentage point. Decrease in the proportion of kids receiving preventive dental care. South, what happened in the South? Yeah, there was an increase. By how much? 2.2 percentage points. And then for the Northeast, what happened? Increase a tiny bit. Just under a half of a percentage point. just under 0.5 percentage point. Remember when we compared the dispersions to the variances? So if you look at the standard deviation column, 3.5 for the west, 2.3 for the Midwest, 2.7 for the South, 2.7 for the Northeast. Not much of a difference in the variances. See, and that's why it shows up as no statistically significant differences in the variances. Okay, so these are our descriptors table. We're going to scroll down a little bit and look at our normality assumption. What does our normality assumption tell us? So here's Shapiro-Wilk. Here's our p-value. It's 0.002. So what will we do with our null hypothesis? Keep it or get rid of it? We have to get rid of it. So we can't assume the data is normally distributed. We're going to assume that it's not normally distributed. So we violated one of our assumptions for the test. We'll see how bad or how badly we've violated that assumption. But for now, we're going to proceed. We're going to move forward. Okay? And just note that our data is not normally distributed.
What does
Yes?
that mean, violated assumption or assumption?
Right, so we have an assumption that in order to be able to do this test, that our data has to fit this map, right? The map is this normal distribution. And we need that map because it tells us what's likely, there in the middle, and what's not likely, out at the ends, in that shape, that bell shape, symmetric. Okay, so we have to find out, does our data fit that map? And the Shapiro-Wilk will tell us if our data fits that map. And if it fits that map, that's great. Then we know what's likely and what's not likely in that kind of distribution. If it does not fit that map, then what we thought would be unlikely might actually be more likely.
So it doesn't fit it.
This is telling us it doesn't fit that map, and we should be really careful about our conclusions. Yeah. If we move forward. Okay, moving on. And now the drum roll for your findings. Where do we find differences? When you look at this table, you'll notice that it's a matrix. That is, we see West, Midwest, South, Northeast, and West, Midwest, South, Northeast as rows and columns. You might be thinking of identity matrix. Oopsie. And I would say yes, identity matrix. Good. And that's why we only see half of this table or matrix filled in, because the other half would just be redundant. Okay, and then when we see West versus West, we'll just see a dash there. Nothing there. Can't compare against itself. Okay, so for the first row group, it's the mean difference, that is percentage point difference between these two regions, the t-value, which is that signal to noise ratio for that two group comparison, degrees of freedom, and p-value. Okay. So the West versus the Midwest, there's a nearly 4 percentage point difference, West above the Midwest. And the p-value is what? 0.006. So there's a statistically significant difference between the West and the Midwest from 2007 to 2016. Good? What about the West versus the South? What did you find there? Nearly a percentage point difference in terms of the West being more than the South. That is a change from 2007 to 2016. And the p-value is 0.827. So this nearly 1 percentage point difference is not considered to be statistically significant. Its p-value 0.8 is greater than 0.05. When we compare the West to the Northeast, there's a 2.6 percentage point difference. That is, the West saw more of a difference or more increase than the Northeast. P-value there, 0.159. Not statistically significant. Okay. There's still other unique comparisons we'd have to go through. Midwest versus the South. Midwest is just over 3 percentage points lower than the South. The p-value there is 0.03, so that's significant. And then when we compare the Midwest to the Northeast, minus 1.36 for the percentage point difference, but the p-value is 0.702, not statistically significant. And then finally, South versus the Northeast, 1.73 percentage point difference, which is kind of surprising that the South saw more of an improvement than the Northeast. But again, if the Northeast was already high, didn't really feel like they needed to move much, maybe the South was lower, and they had to make some improvement. Well, there's a 1.73 percentage point difference, but the p-value there is 0.462, not considered to be statistically different. So where do we have statistically significant differences for these pairwise comparisons? For the West versus Midwest, exactly, 0.006. For the Midwest versus the South at 0.030, and that's it.
So those two would be in that first paragraph.
Exactly, those two. And if you go back to that slide, I should have those two there. And then the others are for the rest, where there aren't significant differences. Yes?
About the south, it's 0.40 something. We don't pay attention to that one?
Yes, we do. So we have to note that, hey, there isn't a significant difference here for the South versus the Northeast.
Why did you Northeast doesn't have that?
Oh, these guys? Oh, that's because the Northeast was already included with West versus Northeast, Midwest versus Northeast, and South versus Northeast. Yeah. So there's nothing there because it would be redundant. And so that tells us what's happening from 2007 all the way to 2016. The idea that if we get this early pre-ACA measure, and then this later after ACA measure, do we find any differences in the proportion of kids receiving preventive dental care? And it says yes, we do. When we compare the West versus the Midwest, there are some differences there. They're affected differently, right? The Midwest versus the South, they were affected differently. And the South versus Northeast, no. So, and everything else, no. Because there are only two regions where we found significant differences in the way they were affected, we're hypothesizing, by ACA in terms of the proportion of kids receiving preventive dental care. But to have greater confidence in that, we would need to look at what's happening 2007 to 2011. Were there any differences? If so, we would need to take that into consideration. And then from 2011 to 2016, we'd like to see maybe these changes were more recent, which would give us more confidence that, oh, these are post-ACA differences. And that's your homework assignment. So what I want to do is I want to give you a 5-minute break, then come back, and then let's look at 2007 to 2011 together. Okay? All right. And then you'll do 11 to 16 on your own.
Like night routines. I knocked out. Oh, wait, I saw it. Never watched I've been doing it a little more than that.
Okay, that's good. Was it because he?
Yeah, it does have some.
Yeah. I don't know. Well, what about it? When I was talking to him. She's gone.
Yeah, I did. I got lucky. Sales friends and even some of the dental students. So he's able to screen them and he was fairly yeah. And I'd rather have just, more of the patient than no patient.
The workbook is good because it kind of gives you a nice picture and it fills in all the gaps. But don't.
They're running She has to have
The assignments.
They're like running tests. That's like chest pain.
Okay, I changed my topic.
I think it's going to be.
Did you see that? That's not. Okay. I think it's done. Just I add one more thing.
But if you have any
Oh my god, I forgot about that.
don't hesitate to come back.
Yes, that's how I can submit it to the campus.
Got it? Because I've only seen 3 patients. I haven't done a lot of practice, to be honest.
I don't know about Thank you so much. Thank you. So I was checking your title. I like yesterday. So for the final exam, like any choice, is there any way that we have something about, the explanation, like paper, and about the other part that it's like we have for midterm, that was about questions and stuff, for final, because you mentioned there was no way that we skip the final and then do the final before that day. Is there any way that we can do it? Means make the final 2 points with Gemini, so we can have it at home like midterm.
Yeah.
If it's possible, I asked them to. I talked to my classmates. They're kind of angry. They're not that much concerned about, I am because I'm not that much okay.
I hear what you're saying.
If it's okay. Now I know.
I'll give that some consideration. I still think I'm going to use the same format as the midterm exam. There's pressure on me to
do it on that date and here.
right then. Yeah, I'll split it so that the movie part is separate from
Really appreciate it. Thank you.
How's it going, sir?
All right, how are you?
I'm tired.
Yeah? I think for some reason everyone's gotten hit with some kind of
Tired bug?
tired bug. So
This is a lot of information though, but
yeah, it's a lot.
we're hanging on.
I can tell. I'm getting questions, which is good. You guys are engaged, so yeah, that's encouraging.
So after the break, what are we going over next?
We're going to do 2007 to 2011, so we get an idea. Again, we're trying to fill in, hey, what was happening before 2007 or around 2010.
And then, do we have any other quizzes or anything coming up?
There will be 1 or 2 more quizzes in that. It'll just be the assignments, the group project, and the
Probably.
And what is the homework stuff do?
at the end of the course.
Okay. All right. Sounds good.
Because what I want to do is while you guys are working on your final exam, is look at that workbook stuff.
Okay.
Do you have the actual book or is yours like PDF? Or
Yeah, almost. Yeah.
How many more much chapters do you have to do in the book?
But she like dealt with it by
As long as I have it,
herself.
It's like small sessions. Give extra.
Right out.
Give extra. The commercials are like,
Sample. This one, right?
wait, what were you about? I don't remember. Get up my thing.
You should,
It
yeah.
doesn't open until.
I wanted to, but I wasn't sure.
You just drop them in the box. Semi-imagination. Why, I'm tempted to go snap.
Yeah, I mean, who doesn't open
For my 30s. Why is my
You know,
patio? I don't know, I've never gotten any. That's the only thing I know.
she might need her I understand.
You missed AJ trying to give his potato salad away to Nikki. She turned it down. Because it was happening today.
I agree.
We had a discussion about food.
Maybe we should, you know, like, ask her, like, for the final, that was final. Yeah. So we don't know much about this, and we're worried about his final thing. Yeah, she said she did. So I feel like that was this year. But we're gonna take not this, we're gonna take that whole year, and we're just gonna be like,
Look at me.
yep, your project is not gonna work. So.
All right, let's do it.
Ready?
Yeah, let's go.
Let's get back at it.
That's too bad. Kevin needs to learn who's in charge.
All right. Feeling energized a bit?
Yeah.
Got some sugar in your system? Stretch the legs a little bit. Do you have a greater appreciation for how much work goes into statistically working with your data to kind of figure out what's going on? This is just at a basic level.
If
Just
it
at a
was
basic
30
level.
years ago, definitely.
Yeah, that's right. It's only, I can tell you, I mean, I'm old, maybe not that old, but I'm old enough that a lot of what we're doing now, we had to do by hand. By hand. So this is a unique privilege to be in, to be able to come up with answers fairly quickly. All right, so we're trying to figure out what's happening from 2007 to 2016, but we're being very cagey about it. We want to split that up and say what's happening from 2007 to 2011, and then from 2011 to 2016. So let's take out our 2007 to 2016 and instead put in 2007 to 2011. This will give us an idea of what's happening before we think the effects of the Affordable Care Act start to kick in. So when we do so, everything that you've selected before is still selected, but we need to make sure that what we want is still valid, especially for equal variances, for that assumption, right? So when we look for equal variances, what's the name of that test?
Fisher.
Levine for equal variances. Fisher will tell us whether the ANOVA has a p-value that we were looking for, but Levine is what will tell us whether our data is normally distributed or, whether we have equal variances or not. And what's the p-value from Levine for 2007 to 2011? 0.182. So is it greater than 0.05 or less than 0.05? It's greater than or equal to 0.05, which means we do have homogeneity of variance. So we can keep our Fisher's test, or the Fisher's assumption, or the Fisher's method for giving us a p-value for our difference between the means. Yes?
So you switched over the years.
Yes. Swap out 2007 to 2016, and we're only going to look at 2007 to 2011 because we want to get an idea of what's happening before the Affordable Care Act. Yes. Levine? Yeah, Levine's is a test of homogeneity of variance. That's our null hypothesis. So if Levine's is greater than or equal to 0.05, then you keep your null hypothesis. If Levine's is less than 0.05, you're going to have to get rid of that homogeneity of variance assumption and instead conclude heterogeneity of variance. So since Levine is at 0.182, we're going to assume we do have homogeneity of variance. So we can go ahead and keep our Fisher's approach for our ANOVA test. And what does the ANOVA test tell us for 2007 to 2011? Do we have differences in the proportion of kids receiving preventive dental care among those regions? Is there a change? Is there significant change for those regions? So it's that top table. We look at Fisher's. What's the p-value there?
Very high.
Right, thank you. 0.6. 0.620. We're going to use Fisher's, not Welch's. Although, would your conclusion differ? No, your conclusion wouldn't differ. But we're going to use Fisher's, and what does that tell us? 0.6. Is there a difference among the means? No, there isn't. So we looked at 2007 to 2016. Did we find a difference among the means? We did. Now we're only looking at 2007, 2011. Is there a difference there among the means? No, which means the regions look really similar. 2007 to 2011. Got it? So if this tells us that the regions look really similar, high altitude, I don't really see any differences down there. Should we run post hoc tests?
No.
No, we should not. We should not. And so if we actually did look at the post hoc tests, no peeking, but if you did anyway, what are you going to find? Nothing good, nothing interesting, no differences. However, this is sort of what we were hoping for in terms of our hypothesis that the Affordable Care Act is what's responsible for differences in the proportion of kids receiving preventive dental care. Yes?
Why we don't do the games hour?
Okay, Games How for the post hoc test is when you have unequal variances. We ran Levine's test to find out if we have equal or unequal variances. And what did Levine's test tell us? Levine's test told us at 0.18 something that we have equal variances. So we're going to use Tukey. But here we're not going to look at the post hocs at all because we don't have any differences that warrant us to look at the post hoc procedures. Isn't that kind of interesting? 2007, 2011? We don't have any differences. I'll let you kind of fill in the rest from there. But are you curious about 2011 to 2016?
Yes.
Well, there is differences.
I'm not curious anymore. Let's put 11 to 16 in. Run me through it. First, what does Levine's tell us? Because are we going to be looking at Welch's or Fisher's for our results? We're going to be looking at Fisher's because Levine says what? What's the p-value for Levine's? Right, insignificant. 0.5 is greater than 0.05. Okay? All right. So if we jump up to the top, what does Fisher's tell us? Do we have differences among the regions? We do. So we saw from 2007, 2016, we said, okay, well, let's be sure. Let's look at 2007 to 2011. No differences. Now we're only looking at 11 to 16, and we've got the differences. Okay, so where are the differences? Well, first, if we look at the group statistics, or the descriptive statistics, the West is at what? 4.08. 4 percentage point difference. The Midwest is at 1. Now, how is that different from what we saw from 2007 to 2016 for the Midwest?
Negative.
Right. We saw a decrease. But if we only look at the 11 to 16, we see an improvement. What about the South? Yeah, nearly 3, almost 3. What about the Northeast? So improvement for all 4 regions, but at different levels. We see the biggest at the West, followed by the South, and then the Northeast and Midwest. Now, we're saying, wow, 4 percentage point difference, 1, 1, 2. I wonder if there are significant differences among these. We can get that, right? Let's look at our post hocs.
Games, Hal, or Tukey for post hocs? I heard games and I saw her shaking their head. No. Tukey. And why? Why are we using Tukey?
Equal variances.
Because we have equal variances. Levine's is telling us we have equal variances. So here, West versus Midwest, about a 3 percentage point difference, nearly. Is it different? Yeah, p-value of 0.01. That's less than 0.05. So here we have a significant difference between the West and the Midwest when we're looking from 11 to 16. What about the West versus the South? 1.25 percentage points. Is it different though? No. 0.454. The p-value is greater than 0.05. What about the West versus the Northeast? 2.6 percentage point difference. Is it different?
Almost.
Technically, right, almost. Technically, we'd have to say no. Right? So if we're greater than 0.05 or equal to it, that's when we say no difference. Okay, but there were a couple lectures ago, I kind of showed you what to conclude or how to describe the different degrees of p-values. And here we were going to say anything from 0.05 to 0.1 would be weak evidence. Not no evidence, but weak evidence against the null hypothesis. So yes, we do have a difference between the West and the Northeast. It's just weak. P-values at 0.05. Technically, not statistically significant, but we're going to call it weak evidence. Okay, Midwest versus the South. 1.74 percentage point difference, but in the other direction, it's lower, but it's not different, 0.197. Midwest versus the Northeast, much less than half a percentage point, not different either, 0.984 p-value. And then for the South versus the Northeast, 1.38 percentage point difference, but not different, 0.469. Too fast? No. Okay. Wait, a little bit too fast?
No, you're good.
No. Good? All right. So 2007, 2016, we see some interesting differences. 2007, 2011, no interesting differences there. Nothing statistically significant. 2011, 2016, that's where we've identified where these differences are. The time points for these are around that Affordable Care Act, so we're feeling pretty confident that these big changes that we're seeing throughout the nation affecting the regions differently is probably due to Affordable Care Act, when we're looking at the proportion of kids receiving preventive dental care. Now, how ACA affects that, we're not sure. It could be ACA, it could be, if we had used different time points, what else could it be? I mean, some have argued that it might be due to the 2008 financial crisis, right? But I think that's too early for us to see these kind of changes where we saw 2007, 2011, no difference. So if this is the financial crisis, I mean, some were hit pretty hard and it kind of lasted a while for families, maybe, but I don't think that it describes what happens from 11 to 16. Any questions? Yes?
How's the final going to be? Is it going to be something similar to this? I know we've talked about it a few times, but understanding more of it now, I feel like I can ask again.
Right. So do you see the write-ups for all the statistical procedures? You have to provide that. That's really easy because it's right there. Essentially, all you have to do is copy that. But you've got to plug in the right variables. You've got to plug in the right central tendencies and the p-value. So you do need to know what you're doing, even though it's kind of written out for you what the conclusion should look like.
So we will
So
have a
can we try
template.
one of them?
We've done it. Yeah.
Will we have a template, like what we have for homework? For the final?
A template for the.
Like, you know, you're giving us a template and we fill in the, are you saying that it's going to be the same way?
Like
You have a
template for the
template?
results.
Oh yeah, I already gave that to you. The slide that shows you how to write
Yeah.
that. Yeah, that's your template.
Final, will it be like that too?
Right. So you have the
Okay.
data. We have the hypothesis that we're testing. But then you have to go to Jamovi, you have to pick up the one-way ANOVA, and make sure you select that, not something else. You have to ask for all these different things so that you can write that slide, essentially. Now, some of the things that you'll need to transfer over from previous lectures, for example, when I ask you to characterize the distributions for these new variables, which we haven't done yet, you would go to exploration, descriptives, you take your 3 new variables, does all of this look familiar? Yeah. And so we can ask about the normality for. Did I not ask for it? It's not there. Here we go. So we can see from 2007 to 2016, it says it's normally distributed, but barely. And then for 2011 to 2016, it's normally distributed, p-value 0.196. 2007 to 2011, normally distributed, p-value 0.291. Right? But now we want to actually look at them, because we want to figure out how homogeneous are these distributions. Do they really look like they're normally distributed? Unimodal, one mode, and not bimodal. So if we look at 2007, 2016, it says it's normally distributed, but it definitely does not look like this is one distribution or one population. It's a distribution, but it's not one population. That's important to understand because our idea here is that the Affordable Care Act created different kinds of sub-regions within the U.S. So if we go back further in time, there's 2011, 2016. Looks a little bit better. But if we look at 2007, 2011, definitely looks like this comes from one population. So again, before the Affordable Care Act, certain health care parameters or metrics, U.S. looked like one country, one population. After ACA, some of these metrics no longer look like one population, they now look like several populations being merged together. Okay? And that's a really important distinction for us to be able to understand and characterize. So I would expect you to be able to do that on the final exam. So if I ask you to compare and contrast these 3 distributions, you should be able to do so. If I asked you to take these 3 and compare the distributions by region, I would expect you to put region in the split by, just like you did at the beginning of the course, but now with new variables, as we get closer to being able to understand what's happening in the country. And take a look here and say, oh, I can see where we have differences from 2007 to 2016. I can appreciate how these don't look like the same population. Right?
What is the negative 50510? What does that represent again?
Oh, what's on the x-axis here? What's on the x-axis? So the question is, what's on the x-axis?
How many kids are getting
Percent changes.
Yeah, this is the percent change from 2007 to 2016. So it's how many of these states are closer to 0 or above 0 or less than 0? And then what's on the y-axis? It doesn't say here. Yes, these are strata, so we know this is region, but what's on the y-axis within each of these strata?
Amounts of states.
Exactly, number of states. So it is number, not dentist, but it is number. Number of states. Number of states that are at that level in terms of the change from 2007 to 2016. So yeah, the regions look very different from each other, 2007 to 2016. How do they compare 2011 to 2016? Yeah, they're still a little bit different, but each region starts to look a little bit more like it's coming from its own unique population. But some of them, like the Midwest, and we saw this before, look like it has a bimodal distribution, which is important for us to understand, since the West or Midwest was the only region that saw a decrease. And then for 2007 and 2011, look a lot more similar to each other, except with the Northeast appearing to be maybe bimodal. So I would expect you to be able to do this for new variables. Again, we're not looking for essays, we're not looking for grant applications. No, a paragraph. 3 to 5 sentences. Other questions? You've learned a number of procedures now. You've got the one sample t-test, independent sample t-test, paired sample t-test, now the ANOVA procedure. We're going to finish up with correlation and chi-square. And you'll be able to properly do the final exam and to work on your group project. Yes?
Okay, back to the ANOVA test. I was
Yes.
just comparing it to the write-up that the template that you gave us.
Yes.
And I'm inputting like 2016 and 2011 just to like see
Yes.
where the information's coming from.
Yes.
How come in the first paragraph we didn't include the Northeast? I know that like in the Tukey post test that it was the same, like it was the same amendment. But for the first paragraph, how come we didn't include the Northeast right there?
So here?
Yes.
Okay, so here is our overall test. And then we're looking at Tukey, and we're pointing to Midwest compared to the West and the South. Now, Midwest versus the Northeast, was that significant?
No.
I don't remember.
Midwest to the north.
Midwest to the... So we have Midwest and Northeast down here. And so Midwest and Northeast is not significant. So I'm leaving this section for where we have significant differences. And everything else, which is no significant differences, we're going to put down here.
Okay.
Because most people are interested in where did you find significant differences. So we'll put that first. Then anything else, any other comparison that wasn't, we'll stick those down here.
Okay. And then for looking, I was comparing the 2016 to 2011.
2016, 2011,
So we
okay?
didn't have any like significant differences. There was like no negatives in the means of any of the regions.
Okay.
So would I just pick the lowest one to make it significantly lower, even though it's not significantly lower?
Oh, I see what you're saying. So if one of these was, let's say, significantly higher, as long as it was significant,
Okay.
I would put it here.
Okay.
But if it wasn't significant at all, I'd put it down here. So I see what you're saying. Yeah. Other questions? Those are good questions.
So do we have an assignment due for this?
You will have an assignment due.
Okay. This
Give
is
me
not-
a day to take from
Okay.
the assistant and upload it. Yeah. But I just wanted to make sure I went through parts of it with you so you have an idea of what you will have to do. Other questions? No? Okay, so you need some time before your next class?
Yes.
Yes. Alrighty. If there are no questions for me, don't hesitate to email me if they come later, or if some of you need a little bit more assistance to kind of work through the assignment together, okay?